Okay, this is the video on 5.3, and this is finding volumes by shells. It's also the place where we look at how do we know what it is? Is it a disc? Is it a washer? Is it a shell? So the first thing they do is they show us some examples on shells and how to work shells, and then I have a whole bunch of examples on discerning which one it is, and then just kind of setting them up. And so let's get to it. Pay-per-view. I've also got my heater on, so I'm not as cold as I was in the last video. I've got some food in my belly, and some more tea, decaffeinated, of course, this time of the night. Be careful. And okay, so, and I got my little friends here helping me make this video. So you're basically doing the same thing. And if you want more examples, I recommend Professor Rob Bob. I also like Professor Leonard, but I didn't get his one of his YouTube pages up here. But this guy has really, really nice drawings. Professor Leonard's drawings are very similar to mine. And so anyway, which is they're not wonderful. So we're going to be finding the volume of the same things. So something like this, finding the volume of it. So we had the idea of slicing it was our idea. But what if it's this way? And I can't get my equations so that I can do that slicing and find those heights. What if I wanted to instead like peel it like it was an onion? And so that's what you kind of are doing with shells. And so people show these kind of things to show shells, because if I was trying to find the volume of this thing, then I could find the volume of this, right? Which would be, and then the volume of this, ignore the bottom, and the volume of this, and then the volume of this. So I'm kind of peeling this like an onion, right, into pieces. And of course, I'm going to make these wafer thin. And so my son Tyler made for me, he 3D printed it, and I really like it. And this is a shape. And if I wanted to find the volume of this shape, right, then what you do with shells, so here it is in the 3D printed mode, the same shape, is that you pull it apart. And so I'm going to find the volume of this, and I'm going to find the volume of this, and I'm going to find the volume of this. And so I've sliced it so that I'm kind of peeling it like an onion. And so I have all these pieces, and I'm going to find the volume of each of those pieces. That's what my idea is. And remember what volume is. It's area times how thick something is what it is. So I'm going to put that over there. I'm going to put that over there so that we can look at, so here's another thing, a tape roll. And if I was trying to find the volume of it, remember I'm pulling off the outer layer. And when I pull it off the way I was pulling it off there, it was making a circular ring, right? So here's my circular ring. But what I want to do is I want to snip that circular ring and I want to pull it apart. And when you do that, then what you're going to notice is this thing is called a shell. And this is what a shell looks like. It's a rectangle. And so if I was to take this, and if I was to snip it here, it's 3D material, 3D printing material, whatever that is. So I can't snip it, but if I was, and then if I was to open it out, it would be a rectangle, is what it would be. And then remember that this right here was the circumference of a circle. And so I'm going to write that right here. This is the circumference of the circle. That's how long this is, which is 2 pi r. And then this right here is the height of my rectangle, and it's called the height of my shell. And so the area, remember that's what you're going to do, is you're going to do the area dx for the volume, just the same way we did before. But the area, instead of the things being circular, this is what they were in discs, they were circular. And what they were in washers is they were circular with holes in the center, right? And so these are the things that I'm having. And so this time when I do it, it's going to be a rectangle. And how you find the area of a rectangle is length times width, which in this case is 2 pi r times h. Okay, so that's kind of the story on that. So this is kind of our idea, is that we're going to splice our shells so that we have a height of our shell. And you saw that I labeled the height on there. And then we have a radius of our shell. And so the circle right here is of radius r, right? So here's the circle that I have there. It's going right here. And so that when I clean this out, when I pull this out, then the circumference, which is the length of my rectangle, is 2 pi r. And so so this time each area that we have is a rectangle, and then the volume would be, and then I didn't give enough room to put the volume, and I think what and I have two equals there, and it's like, you know, when you type something a long time ago, you're like, what was I expecting myself to put there? But what the volume is the area times the width. And when I say the width, I mean this width right here, that width. And it is the thickness. And I think I was calling it thickness before. And so maybe I should call it thickness because that's what I was calling it before. The area, and the area is the, how do you spell thickness? Thi, thickness? I don't know if that's how you spell thickness. And so it's the area times the thickness. And so the area of this is 2 pi RH, right? Because it's this times this. And then the thickness is delta x, which is, that's what we call the thickness. How we're going to set that thickness is our delta x. And you all know that delta x is dx, right? Approximated with dx. And in fact, they told us that, and this was a long, long time ago, they told us delta y was approximately equal to dy, and they told us delta x was exactly equal to dx when we have these up, you know. So anyway, that's kind of that story. I wish I wouldn't have got into that story, but that's our thickness, that's what it's representing. Okay, so here's the method. So there's our little formula. And so here's the method. And I have so much stuff here now that I can't even move my paper up. And so move over, everybody. The basic technique for the volumes of revolution, if you're going around the y-axis or a line parallel to the y-axis, then you need to have your equation solved for y. And we're going to have our area times dx is what we're going to have. We're going to graph everything just like we did with the washers and the discs. And we're going to draw a typical H when we've decided to use a shell. And we're going to draw our R. And we're going to remember that H and R are going to be parallel to one another. Perpendicular to one another. I was trying to say perpendicular. So here R and H are perpendicular to one another. And we'll say what R is and what H is. I'll help you out with that. Give you some advice on that, the way we did on the last one. And if you're going around the x-axis, then your equations need to be solved for x. I hope that you're noticing that that's backwards of what discs and washers are, but don't worry, I have a way of remembering it. I have a way that I remember it, and Professor Rob Bob has a way that he remembers it. And it's different, and whichever way that you want to use to remember it, I'm like, hallelujah, you found a way that goes. And if you make up your own way of remembering it, I'm like, hallelujah, you found a way that goes. So anyway, and so when our equations are solved for x, then we'll have our area dy. And so we're going to give it a try and see how we do. So of course they're telling us that this is a shell here, so I'm not even worried about what it is. I wouldn't ask you to graph this one. I'll just be honest with you on that because it's a cube. But I am going to show you how to graph it, and we'll get it graphed, and then we'll try the shell method on it. So they said, let S be the solid obtained by rotating the region shown in the figure. This is just the directions out of the book about the y-axis. Sketch the typical cylindrical shell and find its circumference and height. use the shell to find the volume S. Do you think you prefer this method to slicing? Explain. Okay, so this is what they're wanting me to try to draw, and I'm just going to be honest with you, I can't draw that. And so, but you don't need to draw that in order to figure out what you got going. Okay, but you do have to draw this. So that's the first thing I have to draw. So in order to get that, to draw that, I would want to pick points. But you know, I probably would factor that just a tiny bit. Y equals x squared, and then this would be 2 minus x, so that I know that when y is 0, and this is the x-intercept, right? When I'm trying to find the x-intercept, I let y equal 0. Then I would know that 0 equals x squared times 2 minus x, so that x is 0 and that x is 2. And, you know, I don't need a great sketch of it because my other line is just the x-axis. I want to know where they connect with one another is what I want to know. And I know that if it's x to the third, it's a snake. And because it's negative x to the third, the snake is upside down. And the other thing I know is that it makes a parabola on 0. So snakes usually start at the bottom and go up like this. But my snake, because it's negative, is starting at the top and going down. So this is probably enough information to draw it. And if I have to pick some points, then forgive me and I'll pick them. So I'm going to put 0 on here and I'm going to put 2 on here. Okay. And I told you that it was x to the third. And because it was negative x to the third, I told you that it was going to come down this way. And because this was a repeated root multiplicity 2, it's going to do like a little parabola looking little thing on that. It's not going to cross through. And then it's going to come back up. And I don't know how high it's going to go. And I don't care, I don't think. And if I do need to know, I'll find it out. And it's going to turn somewhere, and I don't know where, but I could use calculus to find where because that's what we did in chapter 3, but I don't care where. And so, but I do know that it's going to smoothly turn and go back down through 2. Okay. And so this is what it looks like. And then we also have the y equals 0, which is the x-axis right here. Okay. And then it said that it was going rotated around the y-axis. Okay. And so this is my region that's trapped right there. And so all of this other stuff I could erase, right? And not have it on there. And I'm going to be rotating this around that axis. So this problem actually very much looks like this one right here is what it looks like. I have that mound over here, and then and they've already kind of showed me doing the shells on it. But I want to show you how I go about it so that you would know. So I always say like this. I say that if I was going to do a disc washer on it, and that's what I call it, and sometimes I tease and say the dishwasher on it, but disc washer on it, then because it's going around the y-axis, that my integral will be dy, which would mean my equations need to be solved for x. So equations need to be solved for x. The other variable, right? And because it was going around the y-axis, the dishwasher is dy. But the shell, on the other hand, so this is a shell. The shell, on the other hand, is the other variable. So this was dy, so the shell would be dx, which would mean that your equations need to be solved for y, the other variable. So now I'm looking at it. Do I want to do a disc washer or do I want to do a shell? Because I was going around the y-axis, the disc washer would mean I would have dy, which would mean my equations would need to be solved for x. And I don't want to solve this equation for x. And in fact, I doubt that I can solve it for x because it's got the way it is. I'm not going to be able to solve that for x. So I would need another method that doesn't require I solve for x, but it requires I solve for y. And the shell fits that bill. And so that's the reason that I'm choosing to use the shell. Now I know that the volume for a shell, this is the formula, is the integral 2 pi r h, and then in this case dx. And what I have to go, 2 and pi are constants. So what I have to go do is identify r and h. That's what I have to identify. And so this is where my work is going. And so I'm going to come up here and I'm going to identify h. And h is parallel to the axis of rotation. So I'm going to even write that right down here. H is parallel to the axis of rotation. The other thing that I usually say about h, H is, if you're going up and down, is top curve minus bottom curve. If h was going left and right, then I would say it's right curve minus left curve. Okay, so I'm going to draw a typical h in here, and you draw h wherever you want. So I drew mine right in the middle. You could have drawn yours over here. You could have drawn it over here, because there's infinitely many h's, and that's where we're making a slice, is what we're making here to make our shell. Okay, and so right there is my h. And I want to tell people what it is, and I've told you some stuff to help you about h. H is parallel to the axis of rotation. So you notice here's the axis of rotation. So h is straight up and down. It's parallel to the axis of rotation. And h is, in this case, because it's going up and down, is top curve minus bottom curve. And so my top curve was the cubic thing, right? And my bottom curve is the x-axis, which is y equals 0. So that tells me here that h equals, in this case, so top curve, which was 2x squared minus y cubed, right? And so that top curve, this distance from that axis is called y, or called 2x minus x squared, x cubed, because it's out on that curve, right? I can call it either one of those things, but I need everything in terms of x, because dx, right? So I want to make sure I have x, minus the bottom curve, which is 0. And so, yeah, on this one, I really didn't have to worry about the bottom curve, but the next one we might. And so I just thought I would just tell you that. So I'm just going to say h is 2x squared minus 3. And then if you're going around the y-axis, r is really easy. And I'm going to tell you some things about r that I might not write again. And so these are the things about r. R is perpendicular to the axis of rotation, and r is the distance from the axis of rotation to h. That's what r is. It's perpendicular to the axis of rotation. Because the axis of rotation and h are parallel to one another, it's also perpendicular to h, and it is the distance from the axis of rotation to h. So we're going to go up here. Now that distance is probably not a constant. That distance is probably a variable, because remember, h could have been drawn anywhere. So h could have been over here, h could have been over here. So I'm just doing a typical is all I'm doing. So I'm going to draw right here, perpendicular to the axis of rotation and perpendicular to h. And I like to put it at the top, but it would matter not where I put it. I could always draw it to the middle if you wanted. And that right there is my r. And then I want you to remember that the distance from, remember we talked about this, from the y-axis to any point is called x, right? And I want everything in terms of x. And so I don't want to call this, it's meeting that curve over there. But see, it could be here. So it's not just the curve that it is. So there's another H and R situation. And so that distance right there is just X is what it is. And if you're going around the Y axis, it's as easy as that. R is just equal to X. If you're going around an axis other than the y-axis, then it's you have to figure it out. So now I know what h is and I know what r is. So I'm going to put my volume together over here. And so are you remembering what I have, right? I've written those things. So this is my volume. I like to put the 2 pi in the front because it's a constant and you don't have to integrate that constant. And then the r was equal to x. And the h was equal to 2x squared minus x cubed. And then this was dx. And then all I have to do, and then now it's set up, except for I haven't got my bounds. And so I'm going to get my bounds. Remember, your bounds are in terms of x. And what I like to say is they are where you would draw h. And so my typical h's could have been drawn from here all the way to here, right? All the way, H, all the way from 0 all the way to 2. So all the way from x is 0 all the way to x is 2. And then now I have done a beautiful job of setting it up. And all I have to do now, the next part would be to integrate it. They asked me to explain why it would not be good to use the disc or washer. And so the reason it would not have been good to use the disc or washer is I would have had to solve my equation, that equation for x. And I can't solve that equation for x. And so some of them are just hard to solve for x, but some of them are impossible to solve for x. This one's impossible to solve for x. So that's the reason it wasn't good to use the disc or washer. And so here, they didn't actually say on this, I took this directions out of the book, and it actually didn't say setup only. And so I guess I'll integrate it. I want you to know, in order to integrate these, you're going to have to multiply your R and your H together with one another. And so that would be pretty typical. And so this will give us a good example. So the first thing I'm going to have to do in order to integrate that is I have to make it where it's something I can integrate. So I have to multiply this together, which is using the distributive property. So hopefully I don't make a boo-boo there when I multiply. And now that I've multiplied, I can integrate. So the 2 pi I'm trying not to lose. And the 2 holds still. And I add 1 and I divide by 4. And I add 1 and I divide by 5. And that's going from 0 to 2. And 0's nice. And so when I know that the 2 and the 4 would reduce with one another, but this is not my final answer. And so you should always reduce on your final answer, definitely. And so I'm going to be putting in, I know the 2 pi's out here. I'm trying not to lose it, but my top curve is 2 times 2 to the 4th over 4 minus 2 to the 5th over 5 minus my bottom curve, which is 0. And I just plan on putting that in my calculator, and I'm going to let my calculator reduce. So I have so many of my friends telling me that they didn't have to reduce in a previous class. And so what I like to say is that the reason that you have to reduce in calculus is because this class will transfer without taking a test like the AP test or anything else to lots and lots of places like UC Berkeley and Cal Poly SLO and whatnot. And what they like is that we have spent time on reducing. They've told us not to let people get away without reducing. So when you have the advice not to reduce, it's not for me. That wasn't for my class. 2 pi times 8. And that's the reason I like to let you use a scientific calculator, because I think it makes it nice to reduce. I know that they've totally gone away from letting any calculators be used in calculus at state schools like Cal Poly SLO and UCLA. And so I find that kind of funny, but it's true. And so I'm getting the volume is 16 pi over 5. Again, these things are circular because you're rotating them around an axis. And so that creates It creates shapes like this. I know that this one wasn't this shape, but it creates shapes like this. And in creating shapes like that, there you have the circle thing going, and so you're going to have pi because the area of a circle, the circumference of a circle, I guess on this one, that's the circumference of the circle has pi in it. Okay, so I'm going to put a square box around that. See, woo, lovely. Okay. So here they said, this is problem 6 out of your book. Was that a problem out of your book or an example I made up myself? That might have been an example problem that had that used to have the picture, but now they don't have the picture anymore. It makes me really sad. Okay, set up the integral to find the volume of the solid obtained by rotating the region bounded by the given curves about the specified line. Sketch the region, the solid, and the shell. And I, like I said, I don't, these are directions out of your book, and I don't require that you sketch the solid or the shell, but you need to sketch the region. That way you can set it up. And so I'm not good at sketching the solid there. I can't make them look like I can't make them look round, or I can't make them look 3D. And so you don't really need to. And so, but okay, so we get this y equals 4x minus x squared, and y equals x. And so I need to graph that, and I'm like, okay, it's a parabola. And so I probably want, well, two things I'm going to want to know. I'm going to want to know where these two things intersect one another. So sometimes I use my picking of points to find where they intersect one another, praying that it's at a nice point. And the other thing that I want to know is, so not only do I want to know where it intersects one another, I like to know when I'm graphing it, sometimes I like to know what the vertex is. Sometimes I don't care about the vertex here. So let's see what we have kind of going when we start sketching it. And then if I have to erase, forgive me. And because I always want to start lazy, and that's how I am. And so I want to let y equal 0 so that I can find the x-intercept, because I think that's a really good point to find if you have something kind of complicated to graph, particularly if you look at it and notice that you can factor it, like I can this one. And so that happens at x is 0 and at x is 4. And so I'm going to plot those points, x is 0 and x is 4. And then if I need a few other points, I'll pick a few other points. So 0's right here and 4 is right here. And I haven't sketched this one lately, so I don't know if this is a good size, but I'm just going to go for it and think that it is. Because it's minus x squared, it's upside down. So it's a parabola that's doing this, and it's upside down. So I just kind of have a sketch of it. I don't really know how high it goes, and if I need to know that, I'll find it out. If I wanted to go and pick more points, I could. And so now I have y equals x. And so when I kind of sketch this out, it's at a 45-degree angle, right? And it's kind of going through here is where it's kind of going. And so now I realize, well, I do want to know where it intersects right there. And just by my bad sketch, I'm thinking maybe it's at 3. And so, and there's two ways of finding it out. There's to solve it like this. So to solve for the intersection, because I am going to need to know that intersection. And so you can solve it like this. I'm starting to get a scratchy voice. Y equals 4x minus x squared, and y equals x. So they're both equal to y, so they must be equal to one another. X equals 4x minus x squared, right? And then it's quadratic, so I'd want 0 on one side, so I'm going to subtract x. So I get 0 equals 3x minus x squared. Then I'm going to factor out an x, and I get 3 minus x, and so equals 0. And so x is 0, and x is 3. So my guess, even for my crappy graph, was accurate. This is at 3. right? So it's crossing here at 0 and it's crossing here at 3. So even though I didn't carefully plot out points, if you're like, no, I like it when you plot out points, well, plot out points. And that's great. But all I really care about is where they intersect, kind of basically, and what it basically looks like. So this is the region that we have right here. And they're going to rotate that region around the y-axis, they said. So if I was going to do a disc or a washer, so I'm pretending like I don't know what I was going to do, that because it's going around the y-axis, this would be dy, which would mean that my equations need to be solved for x. So I look at this equation right here and I think, can I solve it for x? And the answer is, yeah, I actually could. The other one I could not, but it will be nasty, right? And it will have a square root in it. And I will have to then do integration with a square root, which when I do integration with a square root, sometimes means I have to do a u substitution. And, I don't like to do a u substitution if I don't have to. And so I'm like, yeah, that doesn't seem too easy. And so if I was going to use the shell method, then it will be the other. It'll be dx is what it will be. So I have my memory verse going on. If this is going around the y-axis, then the disc washer is dy. Equations are solved for the other variable. And then the shell is opposite. That's how I have it memorized. Go see how Rob Bob has it. Professor Rob Bob has it memorized. I think that that you might like his just as well or better. And if you like it better, then of course what I am saying is wonderful, right? I just want you to find a method that you like really well. And I'm like, well, my equation is easily solved for y. Both equations are easily solved for y. And so I'm like, I'm not going to use that. And so I'm going to use the shell. So since I've decided to use the shell, I know that the volume equals 2 pi, I like to put on the outside, and then RH. And then this one was dx. So what I need to do is I need to go and I need to find R and H. And I always start with H. And I say to myself, H is parallel to the axis of rotation. So I'm going to go right here, and here's my axis of rotation, and I'm going to draw my H right here. And my H goes from here to here. I usually draw it in the middle, but you could draw it anywhere you wanted. And that's a typical H. And so there is my typical H. The other thing I have memorized with H is when it's going up and down like this, that it's top curve minus bottom curve. So H equals top curve minus bottom curve. Oh, don't run out of room there. So H equals, the top curve is the parabola, which is 4x minus x squared, minus the bottom curve, which is x. And it's kind of lucky that it's a monomial, because if I didn't use the parentheses, I'd get away with it. And I like to simplify H. I'll be honest. 4x minus x is 3x minus x squared. So there's H. And then we already learned that if you're going around the x or the y axis, R is easy. So I'm going around the y axis, so R is going to be easy, and it's this distance right here. It's perpendicular to the axis of rotation and perpendicular to H, and it's the distance from the axis of rotation to H, which the distance, when you do a horizontal distance, that distance is called x. And if it's just going from the y-axis to any point, that's called x. And so this is x. If you're wondering, could it be something other than x, and how would it look then? The next examples, maybe not the very next example, but an example in the future, today, in this video, will show you that. And so it's coming to a theater near you. So we have our volume equals, and this one is just asking me to set up. And so if the integral is easy to do, I haven't decided whether I will do it or not. And so my r is x and my h is 3x minus x squared dx. And there it is set up, except for I haven't put bounds on it. So let's put the bounds on it so we get it all the way set up. Well, we already found the bounds. The bounds are 0 and 3. It's where they intersect, because I'm going to run my h's from here, right, all the way from x is 0 to h is 3, where they intersect. So 0 to 3. And now, boom, I've got it. And so this one's typical because of a shell, is that you just have to multiply that together. So x times 3x is 3x squared. And so we have our volume. And so if they ask me to set it up only, there's my answer. It's a beautiful answer. It's a great answer. It's a lovely answer. It's a perfect answer. There's no answer better than it. And so, but if I'm trying to solve it because I'm practicing my integration, then here I am practicing my integration. The reason I don't ask you to integrate all of them on the test and only integrate some of them on the test is to save you time. And so if you wanted to integrate something, don't integrate something that I didn't ask you to integrate if you're worried about running out of time. And so the 3's would cancel here. And when I do the top curve, that'd be 3 cubed minus 3 to the 4th over 4. Probably should have parentheses there. It's a good idea. And minus 0. And I'm lucky. And so I'm pretty lucky unless I have cosine. If I have cosine, then I have to be careful. And yeah, use your calculator, use your brain, whatever you need to use. And so 3 to the 3rd is 27, and minus, and then 3 to the 4th is 81 over 4. So this is 2 pi times 27 over 4, which is our volume, which is, when I multiply 2 times 27 over 4, is 27 over 2 pi. Pretty typical answer as far as that goes, to have something pi, you know. And so every time I see them, it has pi on the end of it, I think that's right. And then I think, wait a minute, the pi part was just there. And so anyway, so we did a lovely job on that one. That's number 6 out of your book. This is number 29 out of your book. Okay, it says, set up the integral to find the volume of the solid obtained by rotating. Again, we're always rotating around some region around some specified line. In this case, the line is y equals 2. And so I want to get this graphed. They tell me that when you're picking points, to only pick y's to be greater than 0. And so I know that that is a parabola on its side. And x equals 2, I know, is not a horizontal line, a vertical line, right? And so I kind of know what this crazy thing is going to look like. To me, y is greater than 0. It's kind of bounded on the bottom by the x-axis, y equals 0, and then it's only up from there. Okay, so if I go to graph this, do I need to pick a bunch of points on it? Would it be a good idea to pick a bunch of points? Maybe I'll pick just a few, but not a whole bunch. So if I pick y as 0, I would get 0. If I pick 1, I'll get 2. If I pick 2, I'll get 8. I didn't pick any negative ones. And so me not picking any negative ones, this is a parabola, but because I didn't pick any negative points, it's going to be just half a parabola. So I'm going to plot these over here. 0, 0, over 2, up 1, over 8. So if that's 2, that's 4. And that same distance again is 8. And up 2. I don't know if I need all that. Sometimes I draw more than I need, you know how that goes. Okay, they told me, they said that you want to stay up, right? And so really this gives us a line here, y equals 0, and we're staying up. And the reason they didn't want me to draw this part down here is what they didn't want me to do, and then be confused at what area that you're talking about. And then x equals 2, and then I've drawn all this, and x equals 2 is right here. If you were screaming at the screen, you didn't need all of that over there. Erase all of that over there. I don't blame you. And so right here, I'm going to put all dotted in there. Okay. And then I'm going to go around the line y equals 2. And so I'm going to erase this part over here because I don't really need it. And I'm going to erase that up there. And this is at 1, right? And this is at 2. And I'm going to draw that in here, y equals 2. I usually draw it dotted. And I started not drawing it dotted there and realized I usually draw it dotted. And then I just kind of want to clean this stuff up. So I have this right here and here, right, which is kind of a half a parabola. And I'm going around this axis. And so this is going around like that. I'm trying to imagine what that kind of looks like. And it kind of, to me, because I'm going to have that hole in there, as it goes around, there's going to be a hole. And so and then it's going to be flat on this side and then kind of rounded on the inside. And I was kind of thinking that if it was rounded on both sides, it would kind of look like a donut as it went out. But it's like a flat donut. And so anyway, so that's kind of a flat on that outer side. Anyway, okay, so now I want to decide whether or not I want to use a disc or a washer or a shell. And so right here, this is going around the line y equals 2, and I just make a note to myself that is parallel to the x-axis, because that's how I have my memory verse going. If it's going around the x-axis or something parallel to the x-axis, then when I do the disc or washer, it is dx. And when I do the shell, it is dy. This means my equations need to be solved for x. This means my equations need to be solved for y. Vice versa. This means my equations need to be solved for y. This means my equations need to be solved for x. I said that wrong, and I'm sorry. I normally write it, right? Equations, and I say solved for, and because this is x, they have to be solved for y. And then any equations that you have on this need to be solved for x, right? And I normally write it, and then I don't say it wrong. And I'm like, well, this main equation that I have right here, this one here, these I'm not even looking at because they don't have x and y in them, so I'm not even really considering them. Just considering this guy right here is not solved for y, it's solved for x. Could I solve it for y if I wanted? And the answer is yes, I could. And then I could use it looks like it would be a washer because it would be from the axis of rotation coming this way, right? And so, so I would be in error. That would create me having to solve my equation for y, and I'm just not in the mood for that. And shell is my favorite method, and so I like shells better than I like discs, and I definitely like shells better than I like washers. But that's just me. It doesn't have to be you. Okay, so now I want to clean this graph up just a tiny bit, just so that it's just a tiny bit neater, because I want to come in here, and because I have decided to do a shell, which I didn't spell shell all the way correctly, remember that what I need to do a shell, the volume equals 2 pi, the integral, and then RH. And then this one is dy, is what it is. And so what I need to do is I need to go find out what H is. And so I'm going to put H right here. And remember that H is parallel to the axis of rotation. And so when I draw my H in here, I always draw it in the center of this is my region. I always draw it in the center, but it doesn't matter where you draw it. It's a typical H. And so there it is right there, kind of drawn in the center. And notice it's parallel to the axis of rotation. Because it's going left and right, H is right curve minus left curve. Remember when we were finding areas, and we did right curve minus left curve and top curve minus bottom curve, well, that's kind of back, and that's what h is. And I like to always say that's what h is, even if one of them is an axis. Now, one of them is not an axis here, so I'm not really concerned about that. So I'm going from this line right here, which is x equals 2, over to that curve right there, right? And remember, it's right curve minus left curve, so it's 2 minus 2y squared is what it is. And so that's what that curve is. And by doing right curve minus left curve, it sets it up for me perfectly, so I don't have to get into all of this other stuff, right? So it's really, really, really lovely. And so this is what h is. H is 2 minus 2y squared. And usually I would put parentheses there, but because it was monomials, I got lazy and didn't put any parentheses there. Now I want to draw r. And r always goes from the axis of rotation to h. So here it is. There's r. Okay. And if you're going around the x-axis or the y-axis, which I'm not, then r is easy. If you're going around an axis other than the x-axis or the y-axis, you have to think a little bit to do r. Okay, and so because if you're thinking about the distance, remember our things are in terms of y, right? If you're thinking about the distances that you have, and you're thinking that r is equal to y, because that's what it was on the others. It was equal to x, but we were going around different axis, you know. But if you're thinking that's what it is, well, that's a good thought. But here's the deal. And I wish I had more room right here. But this distance right here from the x-axis up to where r meets h right there, that distance right there, this distance right here, which I'll make a little arrow to it, is equal to y. That's what's equal to y. And so really what I have is I have r plus y equals the whole thing, which equals 2. And so when I'm trying to find r, I know that r plus y equals 2. And I'm wanting to say what r is. So if I subtract y both sides, I get 2 minus y. And so it's only easy what r is if I'm going around the x-axis or the y-axis. If I'm going around an axis other than that, then I have to be a little bit tricky. Not a lot tricky. Sometimes I have to be really tricky when I do big R and little r in the disc and washers, but I just have to be a little bit tricky, not hugely tricky. So the whole distance here is 2, right? The distance for part of the way is r, and then the distance from the x-axis up to any point is always called y. That's what that's called. From the x-axis to a point, that's you're going up, you know, and in my plotting an ordered pair, you know, over is x and up is y, and that's exactly what you have going here. Okay, so r is always the distance from the axis of rotation to h, and so now when we go here, our volume equals 2 pi integral r is equal to 2 minus y. RH is equal to 2 minus y squared. 2 minus 2y squared. I missed one of the 2's. dy. Right? Now I got to get some bounds on there, and the bounds are for y because we have dy, and the bounds are for where h would go. And so h could go, I could have drawn my h all the way down here at y is 0, all the way up here to y is 1. And so that's where the y's could go, from 0 to 1. Lovely bounds right there. To integrate that, I have to multiply it together. There's no other thing I can do other than multiply it together. It would be the easiest thing to do anyway. So if it was possible to do a u substitution on this particular problem, then I would say, well, you can multiply it. So why would you even want to do that? That's work, where multiplying it together is not so bad. So I need to FOIL this and then I can integrate it perfectly. If I was asked just to set it up, there it is. It's set up. It's done. And so there's the setup. And so, do I want to take the time to go and integrate it? This video will get too long. I have some over here that are just set up for sure. Do I have some? Yeah, I have tons of them. They go on forever, literally. And so, because you need so much practice at it. And so I really recommend that on the next ones that you start, even pausing the video and trying it yourself. And so I am just going to set this one up, because what you would do if you were going to integrate it, I'll just start you on grading it, and then not integrate it. So this is 4, and then so I'm foiling here. 2 times 2 is 4, 2 times there, so that's minus 4y squared. And so this would be minus 2y, and then this would be plus 2y cubed dy. And then you can integrate that pretty easily, right? Because it would be 4y, and then I'm doing it, and I said I wasn't going to, and you're like, no, don't do it. Put me on faster speed is what I recommend, since I've gotten crazy and can't leave a problem undone. And from 0 to 1, and I could ignore 0, so that's pretty good. So this really becomes 4 minus 4/3. Minus 1 plus half, right? Minus 0. And no, I haven't forgot my 2 pi. So that my volume equals 4 minus 4/3 minus 1 plus half times 2, and then pi, right? 13 over 3 pi. Okay, so we did a lovely job on that one. Okay, so they say set up the integral to find the volume, and they tell us to go ahead and find that volume. And they say that we're going to go about the line x equals 5. So we have this, y equals the square root of x, and we have x equals 2y. And so I have to graph both of those. And so I'm going to do that. I want to know where they intersect one another, so I have the choice of finding that algebraically, or finding it by luck, by picking points. And so I'm going to try to find it by luck on picking points, and then if I don't find it on luck by picking points, then I will solve it algebraically, which this one doesn't look as fun to solve algebraically. So just being honest. So I'm going to pick y as 0, x would be 0, and I'm going to pick y as 1, and then x would be 2. I'm going to pick y as 2, and then x would be 4. And I'm like, I think I got lucky and found where it intersected just by picking a few nice points. And this pencil is done for the night. It says it's too tired to go on, and so I'll have to get this pencil. So we're going to have 0, 0, and then I'm going to have over 1, up 1, and over 4, up 2, being really precise here. And then 0, 0, and then over 2, up 1, and this thing's a line, right? And over 4, up 2, which is here. And ooh, I should use my little ruler. I thought I had a little ruler. Where did it go? To draw this little line. It'll be a beautiful when I draw it with a little line, with a little ruler, the little line. It's going through 0, 0. It's going through there. Because I don't have good scale, it's not perfect. Okay, but I have it. And this right here is at 4 and 0. And then this is the area that's being rotated around. And okay, and what is it being rotated around? X equals 5. So that's over here. So here's 5. I'm going to erase that because where they intersect is done. And I'm going to put a dotted line for the axis of rotation. And then I'm going to make a circle going around like that. And then what I like to write is this is parallel to the y-axis. So that means if I was going to use a disc or a washer parallel to the y-axis, right? Here's the y-axis right here. And so if I was going to use the disc or a washer, this is how I have it memorized in order to set these up. And Professor Rob Bob has it memorized a different way that you might like better. And so I want you to go check out his video and tell me what you like better. And I'm okay if you like his way better. And so I kind of like his way better too, but I can't ever say it. And so right here, if I'm going to do a disc or a washer, this will be dy. If I'm going to use a shell, it'll be the other thing, which will be dx. That means my equations here have to be solved for x. And here my equations need to be solved for y. And I actually have an equation solved for x, and I have an equation solved for y. And so I actually get to choose which one that I would like to do, because this equation could be easily solved for x or for y. And this equation could it's solved for y now, but it could be easily solved for the other, and vice versa. And same here. This could be easily solved for y by dividing by 2. So I would be tempted to use the shell whenever I have a choice. And the reason I would be tempted to use the shell whenever I have a choice is shell is my favorite method. And I hate to use discs and washers. And so, and I know that if I start at the axis of rotation and I go towards my curve, because I'm in air, I'll have to use a washer. And so if I solve my equations for the right variable, I'll have to use a washer. And I have to admit that I don't like the washer method. If I can get away without using it. If it's really the only choice, then that's what I'm going to use. So I have decided to use a shell here, which means that you need to get all of your equations solved for y. So one of the equations was y equals the square root of x. It's already good. The other equation was x equals 2 over y, which I'm going to divide by 2, and that's going to be y equals x over 2. Okay? And then I want you to remember, and I know you do, that h is equal to, because when we draw our typical h, you draw h parallel to the axis of rotation, and I always draw it in the middle. And so my h is really thin right there, but it's straight up and down line right here. And there it is right there, and I labeled it h, and that is top curve minus bottom curve. That's what I let h always be. Top curve minus bottom curve, or right curve minus left curve, depending on if h is going up and down or if h is going left and right. So the top curve is the square root guy. And so this is going to be h equals, and this is going to be the square root guy, minus the bottom curve, which is x over 2. So there's h. And then we're going to do r. And r should have only x in it as well. Everything should only have x in it because we're doing dx. So there should be no y's, only x's. And I'm not going around the x-axis or the y-axis. So that means I'm going to have to think. And so you draw h, you draw your r from h to the axis of rotation. So there's my r. And I know that this is one where I'm going to have to think. And so, because if it's going around the x-axis or the y-axis, you don't have to think about it. It's kind of a freebie. So this distance right here from the, just going straight, drawing it over here, all the way to the y-axis, that distance right here is called x. And then the distance from here to here, from the y-axis to here, is called x. That's always called x. From the y-axis out to any point. Then from h to the axis of rotation is called r. And we know that distance is 5. And we know that x plus r equals 5. And I want to solve for r. So this is going to be 5 minus x is r. Then when I go to put this together, my volume, using a shell, you could have used a washer, is what you would have used, and you would get the same answer. but I'd rather use a shell than a washer. I think they're easier to set up. My R is 5 minus x. My H is not lovely. It's the square root of x minus x over 2 dx. And if they ask me to set it up, other than I haven't got bounds yet, but I am going to get bounds, I would be done. And so my bounds are going to go from right here where they intersect, which is at 0, x is 0, to right here where they intersect, which is at x is 4. So these were their intersection points that I found for free, right? This is where they intersected one another. And I want to know the x coordinates of the intersection, so 0 to 4. If you were doing the washer method, then you would want to know the y coordinates of the intersection, which would be 0 to 2. So this is, I want to know x, so it's 0 to 4. And boom, walla boom, I got it. And this one's not, this would be the answer if they asked me just to set it up. This one's not particularly hard to integrate. You just have to multiply some stuff together, and it is going to be a little bit, tiny bit more annoying than the others because of the square root, right? And so, but not hard still. You still just have to FOIL. So that's 5 times the square root. So that's 5x to the 1/2. And then here, when I multiply, that would be negative 5 over 2x. And then on the inside, that would be negative, and then you would add the exponents. This is 1 as the exponent and half as the exponent. So that's x to the 1/2, which is 3/2. That's where I used to have trouble with my math, as I didn't know 1 plus 1/2 was equal to 3/2. And so now it's really helped me a lot now I know that. And then a negative times a negative is a positive, x squared over 2. You could write that as 1/2 x squared dx. And now I'm going to integrate. So now I've just made it possible to integrate. So I'm going to add 1 to the exponent and divide by the same darn thing. So this is going to be 5. I'm not forgetting the 2x. It's out here. I'm trying not to let it get in my room, in my way. And so this is when I add 1 to that exponent, I get 3/2. And I'm going to divide by, right? So I'm saying to myself, divide by 3/2 is the same as multiplying by 2/3. So that's what I want to do, times 2/3. And then minus 5/2. And then x to the second over 2. And then minus, when I add 1 to 3/2, I get 5/2. So this is x to the 5/2. I left a little room. And I'm going to divide by 5/2, which is the same as multiplying by 2/5. So I'm going to put right here times 2/5. And then plus the 1/2 is going to hold still right there. And then I have x to the 3rd over 3. And I'm going to do that from 0 to 4. And I feel really grateful that 0 is 0. And I'm tired. And I'm not hungry anymore, though, but I am tired. And so I'm not even going to put that together. I'm just going to put it in my calculator. And so I'm going to have 5 times 2/3. And then 4 raised to the 3/2. Go downstairs. Minus 5/2 downstairs. Times. And then in the numerator of a new fraction, remember I was putting in 4 squared. Yeah, you can do some of this in your head because you know 4 squared is 16. Divided by 2. But I'm saying to myself, I'm too tired to even go in my head. And so here I have the fraction 2. Truthfully, I like to do them with my head and with my calculator. And when I'm not too tired, that's how I do it. But when I've had too much, and it's 10 o'clock at night or 11 o'clock at night or whatever time it is, 9:11 at night, then I just go for it. And so this is plus, and then a fraction, and then 1 over 2, and then times, and then we wanted a fraction, and we wanted 4 raised to the 3rd up there in the numerator, and 3 in the denominator. And when I hit equals, I haven't done the 2 yet, pi that's out here, but 2 pi. And then this is that 68? It is 68 over 15 minus 0. So top curve minus bottom curve. So my volume is this number, 68 over 15 times 2, which is 136 pi over 15. And I hope that's right. And I have to admit that I haven't done this problem in a while, so I don't remember if that's the answer. But I know it has pi in it, and so I'm like happy with that. And so if I will go and check these with a solution guide, and because this is problem 28, I can do that. And if I have made a mistake, I'll be sure and tell you. But I hope I haven't. I pray I haven't. And but it's easy without anyone to catch you. This guy right here does not complain when a person makes a mistake. This person just says, okay, you're fine. Then I wrote up a little, is it a disc or is it a washer or is it a shell? But I have been showing you my method all along here, how I decide which one it is going to be. It was just that happened that all of those were nicely done with shell. And so if your equations are solved for x and you're going around the x-axis, then you need to use a shell. If your equations are solved for x and you're going around the y-axis, then you need to use the disc washer. If your equations are solved for y and you're going around the x-axis or something parallel to the x-axis, you need to use the disc washer. And if you are going around the y-axis or something parallel to the y-axis and your equations are solved for y, you need to use the shell. And I mean, it is easy as that. And so come by my office or see me in class, and we'll work on it and drill it into you until you have that down for sure. And so this video is already too long, but unfortunately I have a few more problems and I couldn't help myself because I knew I was going to do videos on them. And so I couldn't help myself but do a whole bunch of examples. And the reason that I did so many examples and couldn't help myself on it is it just takes a lot of examples to get it down. And so, but what I'm going to do is I'm going to call that the end of this video so that I can get a drink and whatnot. And then I'll call the next video more 5.3 and we'll start here, and that will make everyone feel better about their lives. Okay. And so, because this video is already long, I hope that you're pausing and not watching them straight through. And I hope that you're also pausing and seeing if you can do the math yourself. I hope.